I've gotten a lot of comments and interest on how you put together free energy functions and a phase field model when you're using Calphad type free energies. And so even though it wasn't quite on the schedule, I thought I'd give you a little brief introduction to this. And also use this as a context to discuss some of the what is called sharp interface asymptotics, which is used to verify the phase field equations. And so this is multi-order parameter models. And what I think you'll see, so we started at a very kind of basic state. We talked about Cahn-Hilliard equations, we talked about Allen-Cahn equations, and I think what you'll see in this lecture is that essence coming through in something that's really kind of state of the art and things that you can purchase commercially, really. And it's all based upon that same machinery that we put together. And what I'm doing here is following a nice review article that was by Bill Bettinger. Bill Bettinger and many others. And it was in the Annual Reviews Science circa 2002. And it's a very highly cited review article because it lays out the basic ideas very, very, very easily, very well. Chen, that's exactly the same one. Yeah. Yeah, so Bettinger's paper in this article is more focused on, they came from the solidification community, more focused on using free energy functions. Allen-Cahn Chen's review article in the same issue is more focused on people coming from the solid-state phase transformations community. But as you can see, there's significant overlaps. And so we're going to look at isothermal transformations. And so we're going to be dealing with free energies. If you have a situation where you're dealing with solidification, you typically start with entropy production because you have heat flow. Here we're going to assume it's isothermal, so we just have to deal with free energies, which is what we've been doing since the beginning of the class. So that's one of the reasons why I chose this. And so you typically start, what you'll see is a free energy function that looks something like this, where you have a free energy function that's a function of order parameters, composition, temperature. And the temperature is there not because we're going to have heat flow, but because the phase diagram is a function of temperature. dV. So that's typically the starting point. And so we're going to consider a case where we have only two phases that can be identified with different values of the order parameter. Okay, so we have an alpha and a beta phase. We have alpha and beta with order parameter. Zero, one. So try to get things going here. So can anyone see something that's unusual about this free energy function that I've written down here? Look at the symmetry involved in that. So the interesting lack of symmetry is that you'll notice I don't have any gradient energy coefficient associated with the composition, right? I just have a gradient energy coefficient associated with the order parameter. And so what does that mean? You can almost, we don't have to do anything more because you just think about what we did a couple days ago, right? So if there's no gradient energy associated with composition, that means that you can't use this model to do spinodal decomposition, right? Because you're going to get classical diffusion equations. The interfacial energy in the problem has nothing to do with composition, at least gradients in composition. There's no gradient energy coefficient associated with the composition field. Composition will still influence the interfacial energy because it sits in the free energy function. You know, it sits in here. And so it's clear that gradient, the wells and the composition dependence of the free energy will affect the surface energy, but there's no gradient energy coefficient. But one of the nice things about setting up a model like this is that since there's no No gradient energy. In composition, all of the equations will be second order in space. So you only have second order spatial derivatives. So they'll kind of look like diffusion equations. And when you do the Cahn-Hilliard equation, using finite difference methods, you'll understand why that's important, because the time step constraint goes like h to the fourth there rather than h squared for a diffusion equation. So it becomes numerically much easier to solve. And when you're trying to get when you're trying to develop a code that can actually get used in more of an engineering application, you want something that runs quickly and easily and doesn't require a massive supercomputer to get an answer. Okay, and so we already know that if we look at the first variation of the energy and set that equal to 0, we're going to get two equations. We're going to get an equation for the generalized chemical potential, and we're also going to get an equation for what we're calling this. And so we end up with two equations. You kind of know the generalized chemical potential here is just the diffusion potential because we don't have any gradient energy coefficients. We end up with that, just a good old regular diffusion equation. Good old regular diffusion equation. dF dc is mu1 minus mu2, right? So it's just the usual diffusion equation. It's a little more complicated now, of course, because f is a function of the order parameter. So we have a mobility in the phi field. So this is the mobility. MC is the mobility of the concentration field, so I put a C there. M is the mobility of the phi field, so I put a phi there. One thing that I'll warn you about is that in many of these, you have to be very careful when you pick up a paper and you want to use it. In that some cases, and in particular in this review article, they put a factor of a half here, unlike what we did in our work, which basically cancels out the 2 that sits there and just makes the equations look easier, cleaner after this. So you have to be careful what form of the functional that they start with, just so that you don't, because what it does is it changes the expressions for the interfacial energies and the interface widths, because factors of 2 are floating around in the problem. Okay. Yeah. Thank you. Very good. Other questions? Okay, so this looks pretty similar. And so this is pretty clear here that the surface energy is due to K. Is due to the K in the order parameter. Yeah, K in the order parameter, part of the problem of the formulation. So that's really where the surface energy lies. It doesn't lie really in the concentration. Yeah, sure. Right. So what you're getting at is absolutely right. See, and what this model is, it's not a model of a real physical system. It's a computational model that allows you to solve this sharp interface equations. Now that it's really great. We're all on the same page. You know exactly what I'm talking about. So this is a method to compute the evolution of interfaces in the sharp interface limit. It's not a model of a real diffuse interface in a solid-state system. You're absolutely right. You'd need the KC here. Yeah. But that just makes things complicated computationally. So let's see if we can get an interfacial energy in the problem, with only having second derivatives in space in the problem, second derivatives, rather than a fourth order derivative up here. And so that's why this is used. You're absolutely right. No questions. And in fact, the way we're putting together these free energy functions using this order parameter field is rigorous for systems where you have an ordered precipitate. So, for example, in nickel-3 aluminum, the free energy is a function of the composition of the nickel-3 aluminum. It's also a function of the order of the nickel-3 aluminum, the overall order. And so you can actually put together this three-dimensional space that looks reasonably realistic in terms of that individual model. But here, I'm just doing alpha and beta. So this could be solid and liquid. This could be BCC, FCC. Doesn't matter. So we're kind of viewing this as a computational engine, not as a first principles model of a phase transformation, or not even close to a first principles model for a phase transformation. That's a very good point. Other questions? Great. Okay. And so now you understand why we spent the time doing Allen-Cahn and Cahn-Hilliard, because here it pops up, and virtually every model that you use will be based upon this. So if you have a multi-component alloy, you'll have n of these. If you have a multi-phase alloy, you'll have one of these for each phase. So it's all based on the same machinery. So you may wonder why we chose this very specific double well free energy function. Well, that's because that's in fact used in almost all of these treatments. Okay, so the real physics, the real where the rubber hits the road, the real issue is this thing, or in other words, this. And how do you construct this to capture the fact that you have in the real system free energy functions that might look like this, right? Where you don't have this continuity of the free energy function in the composition space, and so that's really the issue. And so what you're using here is the order parameter field phi to interpolate between the free energies of alpha and beta, the free energy densities of alpha and beta. And so it really, the interpolation you might think is it's not meant to be a critical word. It actually is just an interpolation function. That's precisely what it is. And if you wanted to choose, if you look at this equation here, this looks like our good old Allen-Cahn equation. And we know that if we chose a simple double well for f as a function of phi, you can actually determine the interfacial energies and the equilibrium profiles through the interface analytically, right? And in fact, that's what you do. So we're going to take the free energy as a function of phi to look like this. G of phi is going to look like that. And there's our phi squared 1 minus phi squared again, okay? It just pops right up there. And the reason for that is basically because it makes it easier to make headway when you're talking about the free energies of the system, the interfacial free energies in the system that come from this. Okay, we need an interpolation function. That will take, will create a free energy function for both alpha and beta, okay? And There are many possible free interpolation functions. Let me emphasize here. So let's say you have f. You could do it this way. F beta. And you get the idea. When phi is equal to 1, you're in F alpha. And when phi is equal to 0, you're in F beta. And that's a reasonable interpolation function. It turns out not to be very well, it does not lead to very well posed evolution equations. And you need something that's really very, very smooth and has very, very specific characteristics of the derivatives of this function near 0 and 1. And so the interpolation function, rather than that, we're going to use a function that looks rather odd, but it's kind of the standard, one of the standard choices. So p is a function of phi, looks like this. I'll write it again. P is a function of phi. It's going to be equal to phi cubed. Looks something like that. So p at 0 equals 0. P at 1 equals 1, which is what that simple interpolation, really simple interpolation function I just showed you does. But this one has some very nice, very smooth characteristics associated with it at 0 and 1. And the fact that the derivative of p with respect to phi is equal to 0 at 0 and 1 is not an accident. That's chosen very specifically to make sure you get the right answers. Yes. Yeah. 0 and 1. That's right. Yeah. Yeah, hopefully you don't have any order parameters outside 0 and 1. Sometimes happens, so yeah. Yeah. So that's another implementation problem. And so I'm going to, everyone here, most people here, except for a couple, I think, from the mechanics department, are materials people. And so I want to try to develop this in a way that might be palatable for a materials person. And let's go back to our model of the free energy, the Gibbs free energy. When we started the lectures a couple days ago, I wrote this one down here for the regular solution model. All right, so that was the regular solution model, and these are the standard state chemical potentials. They're only functions of temperature, and they are the things that fix the locations of the free energies at 0 and 1. Right, they're related to these intercepts here. And so, if you think about the solid-liquid case, you can in the phase field context, you can kind of use that same idea. And so now we have two phases. Two phases, alpha and beta, or solid and liquid. Solid and liquid. And we have a standard state chemical potential of component A in the liquid state. And we have a standard state chemical potential of component A in the solid state, and they're different, right? That's where you get the latent heat of fusion. And you have the standard state chemical potential of a component B in the liquid state, and a standard state of a component B in the solid state that's a function of temperature. And so these are pure material free energies. And so if you look at F as a function of T, they look like, this is a component A. That's the bulk melting point. And this is the solid, and that's the liquid. And so that's what I mean by these free energy functions. So you have, for the solid and liquid case in the component A, you have the same thing for component B. And you know how to describe the slopes of these things. And the difference here is related to the difference in free energy between the two phases, right? It's just standard stuff. And so here, if you look at this one, if you look at this picture here, you have, again, a solid and a liquid with different free energy functions, right? They're not continuous. And you say, oh, okay, what I'll do is I'm going to take this free energy function and this free energy function, and I'm going to interpolate between the two by adding that axis in phi. So it makes it continuous. So what we can do is we can take the chemical potential, the free energy of component A in the liquid, free energy component A, and just write it as an interpolation function. Fa liquid. And then realizing that you have to have a barrier between the two, you put in an energy barrier. Right? And this is what we were calling A in our earlier stuff. That's the height of the barrier. And remember, G is a function of phi. Looks like this. So in fact, that height there is proportional to WA. Okay? And so this idea of an interpolation function here, where you interpolate from one phase to another, and then you add a well height between the two, appears all over the place. This is like the standard way of interpolating between the two phases. People have different forms of, sometimes they use different forms for what P is, but you always see this general combination of an interpolated free energy and a well. Okay. And so you can do the same thing for component B. So when phi is equal to 1, P of phi is equal to 1, and Fa is equal to Fa liquid. Because remember, G of phi is equal to 0. And when phi is equal to 0, at that point, P of phi is equal to 0, and F is equal to F B liquid. Solid, Fa, sorry. Fa solid. Okay? And G, because G of... okay. Previous case over here. You mean all the way over here? Oh, yeah, over here. Yeah, okay. I mean, this expression that I just kind of... You're talking about this one down here? Yeah, okay. Okay. All right. I'm willing to accept that because I just threw that on there. Okay. Okay. Yeah. Okay. So this is the idea. And then what you can do is that you basically just add a So that's C1. It's over here, this was C1, C2, C1, C2. And then you just add whatever you like up here for the concentration. Blah, blah. And then you're done. And so you've interpolated from one phase to another, from the pure phases, which is where you have the structural discontinuities, in this case the solid and the liquid, and then you just have this form here. Or, if you're using Calphad free energies, this is a little bit harder to do because these concentration terms are very complicated, and sometimes these standard states are in fact very complicated. And so there you can just do the same. It's going to be equal to, you can interpolate on the energy barriers of the two phases, two pure phases. Just C1 minus C, just kind of like what you're doing up here, just same sort of idea. And then just use your interpolation function. Okay, and then just use the interpolation function. It's the same sort of spirit. Here, what you're doing is you're interpolating both in composition and across the pure materials, whereas in the other case you're just kind of interpolating across the pure materials. Okay, questions? So that's it. And so let me talk about some of the results of these models. And I think it's important, even though this is this very simplified example, it kind of captures much of the basic ideas here. So first, let's simplify. Pure material. Let's look at pure material A. And so let's go back. So we're thinking about this plot over here. And you can see that from this plot, this is the free energy of the pure components. The only thing that really matters is the difference between the free energies, right? The absolute value doesn't matter, right? And so what we're going to do is we're just going to set the free energy of the solid equals to 0. And the free energy of A in the solid minus free energy of A in the liquid, solid minus liquid, is going to be equal to so L is the latent heat. And basically, you probably remember, you might remember seeing this a long time back, but let me just sketch what we're doing here. In order to derive that equation, you simply say that the free energies of the two phases are the same, and you assume that the heat capacities basically don't change with temperature. So you get an approximation where you assume straight lines here, and you're basically measuring the difference between those lines. It's kind of from your elementary thermodynamics. And so what that means is that because you have this extra term here, you have this extra term in the free energy functions. Let me go back. Remember, you have the I'd rather than write it over. So if you look at this picture here. So for the free energy of the pure component, we're going to have a double well. And then we're going to have this component. So let's say we're looking in the solid phase. This P of phi would be 0. So you have this, right, this Fa solid. And this Fa solid minus the liquid is going to be given by this. And so you have this extra term that kind of involves this parameter here. And so what you get, what you have is a free energy function that looks like this when you're at equilibrium, Tm, 1. But as you go above and below equilibrium, above and below the melting point, this thing changes sign. And so basically you get the free energy of the solid changing. This, like this, where this is T less than Tm and T greater than Tm. And so you introduce some asymmetries in the wells such that when you're less than the melting point, the liquid phase, the solid phase has a lower free energy. And when you're above the equilibrium phase, the liquid has a higher free energy. And what that means is that you have another driving force in the equations other than diffusion. And that's what I want to emphasize here. Basically, that's the reason why I'm doing this. So we know that the Allen-Cahn equation looks like this. All right, that's the one I wrote down. If you write out the derivative of f with respect to phi, you get the derivative of you get the 2k grad squared phi, and then you get the derivative of the double well, which is this. Yes? So you're dealing with liquid and solid. I missed the last part of that question. What? Yes. Right. So yeah, no, this is so when I first saw this model, that's exactly what I said about 15 years ago. And what it means, so that's I mean, yeah. So again, you're thinking too much like a physicist. Because what it says is kind of important, because it says, you notice there's spinodals here, right? And so this model assumes, or says, if you're thinking about in terms of a physics model, that you get a spinodal decomposition from a liquid to a solid. And that's absolutely impossible, because there's a difference in crystal structure, exactly as you say. Let me kind of So if you look at the, let's say the density as a function of position through a crystal lattice. So in the crystal lattice, you have a periodic density field, and then it decays, and you eventually end up in the liquid. So you have the liquid out here, you have the solid back here. Okay, and if you look at, so you start from this liquid, and you want to create the Fourier components necessary to reconstruct the crystal, you'll find that you need an infinite number of order parameters, not just one. Not just one. So you're absolutely right. That's kind of a theorem in the statistical mechanics community. So what we're doing is we're kind of envisioning that you have this outer envelope of these density peaks that goes from 1 to 0. So we're kind of smearing all this out, and we're going to have this continuous density profile that goes from 0 to 1. And so this is the phase field model. And when you look at this picture over here, we only have one order parameter, phi, that takes you from liquid to solid. And so that you mean you're throwing out a lot of the physics. And what you have to hope is that when you actually run this model as a computational tool, you don't get anywhere near those spinodals, because bad things will happen. And so it's a computational engine. It's not a physical model. So that's, again, you've picked up on exactly the essence of what this is. Other questions? So this is df d phi. This is the double well potential. You kind of know that because it has df d phi is equal to 0 and 1 and at a half. And then you get another term from this free energy function, this difference in the free energies up here. That's L. I can't write it. Sorry. I'm gonna have to ran out of room. Wait a minute. Okay. And so one of the nice things about this is that the partial derivative of p with respect to phi, which you need to compute this derivative here, is going to be equal to 30 times the partial of g, the partial respect to phi. Okay, it's kind of another reason why you chose that really strange interpolation function. And what you end up with is exactly g over here, of course. Phi squared 1 minus phi squared. But the important point here is that you have this difference in melting point between the different temperature between TMA and T. And you have the mobility here. Okay? And so if you think about what this means is that when T is equal to Tm, when these two things are equal, this disappears. And then you have just this, right? And you recognize that, right? That's exactly what we did a couple days ago. So you get the interfacial energies, you get the interface thicknesses exactly as we computed here. If T is not equal to Tm, what happens is that d phi dt is never equal to 0 if T is not equal to Tm. And so this begins to evolve. And so the difference in temperature between the melting point and the actual, between the actual temperature and the melting point generates motion here. And so this is non-diffusive motion, right? So there's no conservation of solute here. It's just if I give you a temperature that's different than Tm, this is going to start moving. And so this is why people, the reason why this is important is that this captures the interfacial kinetics. Excuse me? Yes, exactly. It captures the interfacial kinetics of the evolution problem. But does everyone know what I mean by interfacial kinetics? Okay, let me give you an idea. So, so local equilibrium. Let's say you have a growth of a spherical particle. Oops, sorry. It looks like this. So local equilibrium implies that the let's label this as beta. That's alpha. Local equilibrium implies that the interface mobility goes to infinity, or in other words, the material, the alpha and beta, at the interface are in equilibrium. So what I mean by that is that if you take an atom in alpha, it jumps over into beta, and to get beta to grow. But what local equilibrium says is that the growth rate of beta is so slow compared to how fast the atoms are bouncing back and forth across the interface that this becomes essentially equal to the chemical potentials of the atoms at this interface are equal. So U alpha, U beta of each of the chemical potentials, which implies that the compositions at that point are C beta E and C alpha E, which are given by the phase diagram. Okay? So that's when the interfacial mobility is very, very high. If the interfacial mobility is not very high, what happens is that the atoms begin, that mu alpha is not equal to mu beta anymore. And that implies that the compositions change. Mobility of the interface. Yeah, and you might think this is a digression, but it turns out to be really important in terms of a phase field model. And so what happens there is that as the mobility gets slower and slower, it gets harder and harder to move the interface. Okay, that's what you want to think about. It becomes harder and harder to move the interface. There's more and more drag. And so what happens is that the diffusion rate of solute becomes faster or easier. And so in the limit where the mobility basically goes to essentially zero, the solute field looks like this. There is a gradient. It's non-zero, but very small. In fact, if the mobility is zero, the interface doesn't move. And in fact, yeah, the interface doesn't move, and you just have a compositionally uniform alpha phase. If you let a little mobility, if you allow a little mobility, what will happen is that the atoms will diffuse down, but this composition will not be given by the equilibrium composition. And why is this so important? Why do I keep emphasizing this? And it goes back to exactly the questions that you've been asking. Is that there's a difference between the physics model and the computational model. If you look at a real interface, this is in fact what goes on in a real interface. The interfaces always have a finite mobility, and if they grow fast enough, you're going to be getting differences in composition at the interface from what's given by the phase diagram. However, in a vast majority of phase transformation problems, in solid and liquid transformations, for example, solidification at reasonable rates, solid state phase transformations at reasonable growth rates, this local equilibrium approximation is a very good approximation. And you want your computational model to give you these equilibrium compositions, not this thing that's a function of the mobility. Okay? And the reason why I emphasize that is let's go back and look at what we have here. We have an order parameter field that's going to evolve in time with something related to the mobility of the order parameter field times the difference in temperature at the boundary. And so this thing here is related to the mobility of the interface. As you cool below the melting point, this interface will move even though kind of independently or related to the diffusion of heat in the problem. So this is a mobility term in the phase field model that occurs naturally when you just say that those free energy functions have this temperature difference. And the real problem from a real challenge from a phase field model is that often you don't want this mobility, but you do want the fact that this free energy function changes as you go above and below the melting point because there are different stabilities to the phases, right? And so I'll talk a little bit about that at the end as to how to keep this physics but get rid of this mobility effect. But mobilities are really there. It should be there in the real physics of the problem, but in many cases you don't want it because it just becomes really challenging to do the computations. Okay? So that's my little digression about mobilities and phase field models. Again, motivated by the fact that these are computational engines and not necessarily physical models of the problem.
I can't model interface control flow, right? Diffusion control flow is
Yeah.
So how will those functions get model?
Yeah. So if you take these terms out of the problem, you get other problems as well, potentially, associated with the fact that you won't necessarily have the heat flow and the transformation directions appropriate for when you're above or below the melting point. So it's kind of a catch-22 in many cases. You really do have to put them in. Yeah. They're certainly not in the Cahn-Hilliard equation, right? So you're right in that sense, yeah. Okay. So T is equal to Tm. We have all the results that I gave you that we derived at the beginning. 1 minus tangent. 2 delta. We have an interfacial energy that's proportional to WA times K to the 1/2. And we have an interface thickness that's proportional to K divided by A to the 1/2, okay? WA. Okay, so that's what we have before. So if T is not equal to TMA, not equal to 0, and in the limit of small delta, small interface thickness, you can show that this looks like Tm minus T, where mu A is the so-called mobility, and that's given by M. Tm. Okay, and so you want to think about this mobility. The reason why this is important and interesting is that the mobility of the order parameter field, is related to the actual interfacial mobility of the interface. And that's a real effect. That should be there. But I think what's quite clear is that now in your phase field model, you'll have these interfaces moving at some velocity v, and as long as m is non-zero, you'll have some sort of deviations. M is not infinity. You'll have some sort of deviations in the temperature, right? And so you'll never get this. So in other words, the solid won't grow at the equilibrium melting point. It'll grow at some below melting point associated with the mobility. So that's kind of an issue, but it's embedded in the phase transformation problem. And you also get at T is equal to Tm, small delta. You get the where LC is equal to the capillary length, which is proportional to the interfacial energy. This is a so-called Gibbs-Thompson effect. Gibbs-Thompson effect. And so you notice I said small delta here, and that basically is a way of taking these two phase field equations, this one, this one, and the diffusion equation, written with all these complicated free energy functions. I mean, to get the diffusion equation, I haven't talked much about that, but you can see you just take df dc, and so this will be a function of phi, right? That'll be a function of phi. So there'll be a coupling between these two equations, because this is going to be some function of phi after you take that derivative with respect to c, right? Let me just show you here, right? So phi is embedded in these things, or phi is here, and you take the derivatives with respect to c, okay? And so those will be in the equation. So it's a complicated coupled set of nonlinear partial differential equations. And what do I mean by interfacial energy being small? Sharp interface asymptotics. And so what you do in these sharp interface asymptotics is that you have Let me just sketch the interface here. Zero and 1. You have an interface region. Let's say an interface that lies at near phi is equal to a half. So these things so the sharp interface model looks like that for alpha, beta, and everything else. And the phase field model looks like this. There's a certain delta associated with this. And so there's an outer region, and there's an inner region. Outer and inner region. And what you do is you write an expansion for various parameters, say temperature. Let's say C in a series. With a small parameter. Parameter epsilon in the inner region. And you basically do that by coordinate stretching. You scale the space by that small parameter. Oh, C. So you can write C as where C1 and C2 are the perturbation terms. Remember, we did something like this when we did the Cahn-Hilliard equation, right? But what you're doing here is using a stretched variable, stretched spatial variable. Divided by epsilon. So you expand out this inner region in there. And in the outer region, and epsilon here is on the order of, is related to delta. In the outer region, you also expand. You expand, but in different variables. In non-stretched variables. And you also write C is going to be equal to C0 plus delta C1 plus delta delta squared C2 dot. And then you match inner and outer by letting x tilde go to infinity and x, the regular x, go to 0 from the outside. And so you let the from the outside. I can't reach up there. So from the outside, the outer solution, you let that go to 0, and the inner solution, you let that go to infinity, and they have to match at some boundary. And so the outer variables are kind of on the diffusional length scale. The inner variables are kind of on this delta length scale, And the first person to take these kind of Cahn-Hilliard equations and Allen-Cahn equations and do these kind of asymptotics was a fellow by the name of Günter Kajanalp, and he was in Pittsburgh, near where Jim Langer was working at the time. And one of the interesting things that he found is that by doing these asymptotic expansions and the Allen-Cahn equation and the Cahn-Hilliard equation, you can get these kind of equations. And so if remember when I derived the motion by mean curvature from the Allen-Cahn equation, right? I said, well, we're going to take this function for the free energy, and we're going to assume that the interface is sufficiently flat that I can replace the value for a flat interface, right? That's non-rigorous. The rigorous way to do it is using matched asymptotic expansions. So you can match the inner and the outer. And what you will find for the Allen-Cahn equation is that, in fact, you get V is going to be equal to minus the mobility times the gradient energy coefficient times H. So you will get that out of this matched asymptotic expansions. It's, for those of you who have never seen this before, it's completely opaque, so I'm not going to go through them. It doesn't help. For those of you who have seen them before, you kind of know what I mean, and you could probably do it when you leave here. But it's the reason why I emphasize this is that it's a way of making the connection between the sharp interface model that you know what you want and the diffuse interface model that you're putting together. And it's even more important in this case because remember we had this discussion about whether these are physical models, right? There's no physics in these models in terms of the details of the phase transformation. So you want to make sure the only post that you have to stand on is that these phase field models that, like the one I put together here, not some others, but like the one used for with the Calphad free energies, recaptures the sharp interface model because you know that's the right answer. Okay? And so that's why these asymptotics are not just kind of an academic curiosity. It gives you the touch point to understand that these things are actually worthwhile and realistic models. And why is that such an important thing? So let's look at the model. Model I just wrote down. Okay? Consider the model I just wrote down, which looked pretty reasonable. You just do an interpolation function, blah, 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 blah. If you do the matched asymptotics, what you find is for the mass conservation equation, you get something that looks like this. Oh, that's solid and liquid. Sorry, hold on a second. Dot N. So if none of this looks familiar to you, you should know that the sharp interface result so that's the sharp interface result. And this is the one that you know. It basically says that there's a mass balance, mass conservation or mass balance at the interface that says that the flux into the interface is balanced by, is what gives rise to the velocity or growth of a particle. So if you look at this picture here, so mass diffuses down, you have a concentration gradient, so you have a flux into the particle, and that flux into the particle divided by this difference in concentration gives you the velocity. And when you do the matched asymptotics on that equation I just gave you, you end up with this equation. And there's some extra terms. There are extra terms. So the first extra term is Vn, or kappa, is going to be equal to 2 times the mean curvature. And gamma is going to be the excess component I associated with the interface. The excess component I associated with the interface. And what this term really is an interface stretching term. If you take an interface that has a certain thickness, it has a certain mass associated with it, right? And say that it grows at some later time, it sits out here, and you can see that the interface has gotten bigger. And for it to get bigger, you need more mass in the interface, right? And where does that mass come from? It comes from the bulk phases. And so that's what I mean by interface stretch. So the mass, rather than just feeding the growth of the phases, feeds the growth of this interface because it's so thick. And in fact, it's clear that as the interface thickness here goes to 0, that term disappears. And so if you want to use the realistic interface thickness of an alpha-beta interface or a solid-liquid interface, you won't have any problems. If you want to use interface thickness that's in the order of microns, and the precipitates are on the order of 10 microns, this is a problem. The other interesting term is this. So this is interface stretching. Whoops. This is interface stretching. Stretching. And then you have the term that looks like this. And this is surface diffusion. So you have in here, because you have so much mass, the chemical potential varies with position, let's say, from one position to another. And that gives rise to changes in the morphology of the particle. But it also gives rise to diffusion in the interface. And so you end up with this interface diffusion term that shouldn't be there as well. But again, as that interface thickness goes to 0, as delta goes to 0, and go to 0. So those terms disappear. This is the surface divergence of the surface flux, surface divergence of the surface flux, surface divergence of the surface flux. Those terms disappear, and so you end up with a model that captures that's right when you're looking at the actual physics of the problem, but it's completely wrong when you're using it as a computational engine with interface thicknesses that are too thick. And so the problem, therefore, is devising a phase field model that yields this term without these and still allows you to use deltas here that are much thicker than the actual thickness of the interface. And there's been some, if you look in the literature, there's a lot of work on this. And in fact, you want to use the asymptotics that interface thickness times h is much, much less than 1. And then what people do is that they change these evolution equations, in order to knock out these terms. And so one of the ways of doing this, you'll see, is in the solidification community, is by Karma, and they put in this what's called an anti-trapping term. Anti-trapping term that cancels out some of the fluxes. They choose parameters such that the interface mobility is equal to infinity. So they devised a way of using these phase field equations, but they choose the parameters such that you get local equilibrium all the time without these effects due to the mobility, which is an artifact in many cases. The anti-trapping term gets rid of some of these stretching terms and the interface diffusion terms. But everything has to be chosen very delicately and very carefully. The other thing that I'll mention about this, which is kind of an interesting sidelight, is that when you put in the anti-trapping term, the phase field equations are no longer variational. The total energy of the system is no longer minimized as a function of time. It actually goes up. But the reason why you know it works is because you get the sharp interface equations. So the asymptotics say you get the sharp interface equations. The actual evolution equations violate the first and second laws. And this anti-trapping term is embedded in just about every kind of commercial phase field code now because of all these problems. The other thing is that how do you control I'll mention this and then we'll stop. I mean, how do you control the interfacial energy? Why is that important? Well, if you go back to here, here, you see that the interfacial energy is a function of WA kappa. And as you get these interfacial free energy, as you get these models more and more complicated, this thing becomes functions of the bulk energies of the system. And so as you play around with the bulk free energies, you begin to change the interfacial energies. And so you don't have an independent handle on the interfacial energies compared to the bulk energies. And that is fairly well worked out. And this is the grand potential formulation. It's probably the easiest thing to do. You can look at some work by Kim. And some earlier work by Steinbach. There are some names associated with this that allow you to keep control sigma, control the interfacial energy independent of the bulk free energies. Independent of the bulk free energies. So there are ways of getting around it, but as you begin to add more physics, and so as soon as you add new physics to your problem, as soon as you add anisotropy, as soon as you add more complicated thermodynamics, you start having to worry about the basic formulation of these problems in terms of these kind of artifacts, because you're not really doing any longer the real physics of problem. You don't want a real physics. Actually, you don't want a real physics representation of the system. You want this computational engine that's very efficient. So questions? Comments? Yes, please, go ahead.
There is also a kinetic Wisconsin with the velocity.
Yeah.
And the other term that you could look like that.
Yes. Yeah. So what people will do, so this is at the equilibrium melting point. And if you have a non-zero interfacial velocity, what you'll do is you'll divide by mu a, and that becomes t, and you'll just add it to this equation. So you'll have a departure from the equilibrium melting point given by this. And so you'll get t is equal to tm plus d divided by mu. So that's, that you just add it to that equation. Other questions? Other comments? Questions? Yes, please. Yeah. Yeah. There's this approximation of what? I mean, so the sharp interface model, the reason why you want to compare to the sharp interface model is that in most systems, in many cases, not most, in many cases, you're doing phase separation on length scales that are big compared to the interface thickness. So that's why the sharp interface model is helpful. If you're doing phase separation on the order of nanoscale, you don't have to worry about this because you can actually calculate what the real interface thickness is. And so we recently did a calculation of phase of nucleation in nickel-3 aluminum, and we're interested in the very earliest stages of the nucleation process. And so our computational box was 100 nanometers cubed, 100 nanometers by 100 nanometers. And so there was interface diffuseness, and that's fine. We actually set it to what the interface thickness you measure using an atom probe experiment, and went ahead and did the calculation. And so we got realistic interface thicknesses. And so it was a ternary alloy using Calphad free energies, using diffusion coefficients that are functions of composition that you get from a Calphad assessment of diffusivity. And nickel, aluminum, chrome is a ternary. And we had about a 100 micron cubed box. And that one calculation took about 3 weeks on 300 processors. And so you're never going to do 1 micron cubed with real interface thicknesses. It's not going to happen even on exascale machines. But for those of you, if India ever gets an exascale machine, you have a great grand challenge problem for India, is to actually do one of these huge phase field calculations. Yeah. How do you get a value of mu? Oh, WA? Oh, yeah. So what you do is that you measure the interfacial energy. You look that up in a book, and then you choose in your computation a delta, and you're done. 2 equations and 2 unknowns. You're calibrating from the experiment. Yep.
So like it is almost why are we care about whether interfacial energy suit up or not? Why KKS model comes into picture? No need.
Oh yeah. So the nice thing about the KKS model is that if you look at so the KKS model is that you can fix that sigma is in fact only equal to WA. It's not a function of any of the bulk free energies. And so if you think about this in terms of a Calphad kind of representation, you have a Calphad database, and then you have these complicated free energy functions. You suck those free energy functions out of the Calphad database, and you can fix the interfacial energy, and it doesn't change. Whereas in the let's say you're doing the spinodal decomposition problem. Let's put a sharp point on this. If you're doing the spinodal decomposition problem, you saw that the free energy function is intimately related to the interfacial energy. And so there, if you call a different free energy, if you change the free energy function, you're changing the interfacial energy. And so you have to go back and change the gradient energy coefficient, and also it makes things more complicated. Yeah, that's right. Other questions, comments? Why the composition of functions of mobility? Yeah, this one here. Yeah. So if you look at this term here, it says that the velocity is going to be given by the deviation in the temperature from the melting point, and basically this law can be derived by just saying that the velocity is going to be given by some constant times the change in the free energy of the atoms going across the interface, right? So in the case that I've sketched here, where you have composition case, the velocity is going to go like minus a mobility times delta G, where this is the free energy change on taking an atom from one phase and putting it into another. And if you Taylor expand that delta G and write it in the simplest form, it's going to look like it's going to look something like that, where you just have a linear term in composition. And so if the velocity is non-zero, C can't be equal to C beta E. And so it depends upon this mobility coefficient here, how big that is, depending upon, for a given velocity, V, how big this concentration difference is. And so for very low velocities, if I fix V, and if you have very low mobilities, that means that this difference has to be big, and that moves this thing up here. And if M is very large, if I fix V, then this difference can be small, and you can still get large velocities. So that's why this moves up and down. And it's basically this idea that this is the free energy change of taking atoms from this phase and putting them into this phase. To first order and delta G. And in things like ferrites and things like that, those are big terms. Those are important. Yeah. Other questions? Okay, very good. That was a great discussion. I appreciate all the questions.
How the interpolation function was to be affected by increasing number of years?
Yeah, it does. I'll refer you to the papers for that. I think it can get very complicated very quickly, and there's some interpolation functions that work better for others under certain conditions, and there's a large literature on this that I really can't even begin to summarize easily. But that's something you have to be very careful of. And so each group seems to have its own interpolation functions, and you have to read them carefully. The Kim Suzuki papers, for example, the KKS papers, have very specific constraints on what these interpolation functions can be. And Nellie Mullins has written some interesting papers on extensions and changes that she might recommend. So, okay, questions? Okay, very good. Break time, so we reconvene in about 45 minutes. 11:30. Yep. Okay.